Morning guys, this is the video lecture for Physical Science, Chapter 4, Section 3. We're going to talk about the first law of thermodynamics, the law of conservation of energy. We're also going to talk about power. All right? Power is just the rate at which energy is transferred over time. So it's going to be a really easy math part here. And the concept is something we talked about when we talked about that. We talked about kinetic energy versus gravitational potential energy when we did the egg drop, but we're going to expand on it a little bit. This starts on page 120 in your textbook. All right, so as we mentioned last time, the law of conservation of energy is one of our conservation laws, so it's super easy. It states that energy cannot be created and it cannot be destroyed. It can only be transferred from one object to another. All right, and of course, God is the only one that's able to break any of those conservation laws, and we attribute those as miracles due to his power. Right? So the law of energy is how we convert one form of energy to another. As I mentioned in the last video, that's work. Right? And the rate at which work happens is how we get power. Right? Mechanical energy of a system is the sum, so the combined total of the kinetic energy in the system and all the potential energy in the system. For us, we're going to look at mechanical energy, so we're going to call this ME. Both of those are capitalized, so it's not me, equals kinetic energy plus gravitational potential energy, because we're not going to worry about any of the other kinds of energy right now. There's a lot, but we're going to keep it simple. All right? So the two things I want you to think about are projectile motion and swings. Right? With a projectile motion, we've got this kind of thing, and with a swing, you've got a few different states, right? We'll call these the three positions of a swing as it goes back and forth. All right, so projectile motion. When it starts off, right as it's launched or thrown, it's going to have high kinetic energy, right? Because it's moving really fast. The mass isn't going to change this whole way, so it's only its speed that we're concerned about. And since it's close to the ground, it's got low gravitational potential energy. So because height is low, but speed is high, it's got high kinetic energy and low gravitational potential energy. As it ascends, it increases in height, and it slows down as gravity starts to pull it back towards Earth. So the kinetic energy goes down as speed goes down, and gravitational potential energy increases as height increases. All right? Eventually, the vertical part of that acceleration is going to be zero. So it's no longer going to be traveling vertically, and it's going to start decelerating vertically or traveling faster towards the Earth. Right? So as it goes closer to the Earth again, we've got height decreasing. So gravitational potential energy goes down. But the kinetic energy goes up because it starts to speed up as gravity pulls on it. So high kinetic energy, low gravitational potential energy, high gravitational potential energy, low kinetic energy, high kinetic energy, low gravitational potential energy. All right, as we look at swings, we can model this same thing, right? When you're at the top of a backswing, your height is very high, so you've got high gravitational potential energy, and you're slowing down, so you've got lower kinetic energy. When you're at the bottom of a swing, while you're swinging, not as you're stopped, you have very low potential energy, and your kinetic energy is high because all that height has decreased, but the kinetic energy has increased because you sped up. And then we'll slow back down again. All right? You can see a breakout of both of these on page 122 in your book. I really like the way the book words them. I may be uploading a secondary video to talk about this a little bit further. I haven't decided yet. All right. Moving on, we're going to talk about power. And power doesn't really care what kind of work it is. All right? It doesn't care what type of energy is being used. Okay? Could be electrical, could be chemical, could be somebody carrying something down the hallway. All right? Power is energy divided by time. So we're going to use a capital P for power. that equals energy, capital E for energy, times a lowercase t, all right? Energy is going to be in joules, so that's how we solved for kinetic energy, that's how we solved for gravitational potential energy, so it's still in joules. Remember that it could be kilojoules or millijoules, but we need to flatten those back out to the base units. Time has to be in seconds, no hours here, all right? We're not going to do that one, all right? So energy must be in joules, time must be in seconds. This is going to give us a single watt, W-A-T-T-S. It's a capital W for the units, all right? And 1 watt is the power to do 1 joule of work in 1 second. All right, something else you'll see, and I just want to talk about this a little bit. Your book doesn't use this very often, but I want to show it to you because it does come up. Power can also be defined as the amount of work done in a certain amount of time. Okay, and work is going to be in joules again, time is going to be done in seconds, power is going to give us watts. So same concepts, it's just instead of energy, the rate at which energy is being done, it's the rate at which power is being done. All right, it's just something I want to show you. No matter what, if you're given a math problem with joules and seconds, you can find power, right? Because these are both in joules, these are in seconds, these are in watts. All right? Just something I want to expose you to. Don't want you to get too concerned with it, especially now when I can't really walk you through too much stuff. All right, so we're going to go to page 126 in the textbook, and we're going to do number 26. Number 26 reads, if a runner's power is 400 watts as she runs, how much chemical energy does she convert into other forms in 10 minutes? All right, so this is exercise, so she's converting some of it to kinetic energy, she's converting some of it into heat energy as her body warms up and sweat evaporates, that kind of thing. All right, so it gives us power at 400 watts. So we plug that in where P was. All right. And it says how much chemical energy does she convert to forms in 10 minutes, but remember I need time in seconds. So 10 minutes, 2 seconds, it's 60 seconds per 1 minute. So 10 times 60 is 600, right? So that's going to equal energy divided by 600. And my units are going to be seconds. All right, so put this in your calculator, try to do the algebra, hit pause. When you're done and you have an answer, go ahead and hit play again. I'm just looking at where I wrote the answer so that I don't have to do the math again. All right, so watts multiplied by seconds gets us to joules, because this is joules per second, right? 400 times 600, 240,000. This is one significant figure, and that's one significant figure. This is 2. So let's do a little bit of rounding. And yes, I know that does mean we just lost 40,000 joules, but because of the precision in these two numbers, that's what our math is telling us, all right? I want you to go ahead and take your time with this stuff, all right? If you have questions, let me know. Send me an email, put a note on the Google Classroom assignment, any way that you can contact me to get help. Have a good day, guys.